Okay, hi everyone. So first off, it's sad for me that less people are attending to the class. I think it's good for you to attend the class, although the sessions are being recorded, but it doesn't mean that it's not good to be in the class. I think you can learn more by being in the class and ask questions, participate in the discussions, challenge me and answer questions and these things. I hope that more people attend to the lectures. This is my hope, although it's not mandatory, but I strongly recommend you to participate in the class. And as I had said, participating in the class and having discussions, participating in the discussions, asking questions, answering questions, these will have bonus point. Okay, that's one thing. Another thing is that here I apologize. I just noticed that there are some questions in the Q&A of Teams. I don't know why I didn't, although I had checked the Q&A part, but I hadn't seen them. Teams was not showing to me, but now I just realized that there are several things in the Teams. I apologize. I will assure you that this won't happen again. I will try to be responsive as much as I can. Every night, I think I'm gonna check Teams, and I'll try to be responsive in the same day if it is possible for me. So, so let me go through the questions on Teams. Let me see. So there is Ali Reza has said, hi, I have a question, but what's your question, Ali Reza? Could you please, I think Ali Reza is not here right now, but yeah, please feel free to write your question and I'll try to answer it as much as I know. After that, Column has said, Column, I again apologize that I had not seen your
I
question.
asked at the last lecture, so we don't need to cover that now.
Oh, okay.
Because you
Okay.
hadn't seen it, I figured
Sure.
you had the
Yeah.
opportunity, so I took it
Yeah.
there.
Yeah. Okay. Sorry about that. But for people to have the answer, I will write the answer after the class in front of your question. But this means that even you have said that it might make the problem infeasible. I don't think so. So as you will have it in the cost, even if the profit of the other parts becomes zero, then it means that the company will not only won't it have any profit, it will lose something. So it doesn't make the problem infeasible. So feasibility and infeasibility in optimization means that the domain of the X, the domain of the optimization variable. So if there is no domain, so in other words, if the intersection of the constraints becomes empty, then the problem is infeasible, right? So yes, that's the thing. Is that clear, Column, right now to you?
Yeah, we talked
Yeah,
about this last time because when I
yeah,
first read it, I interpreted that the fixed
yeah.
profit was a constraint rather than an element of the initial problem. That was my confusion.
Okay, sure. And also, Ugam, I apologize that I didn't. I'm gonna after class. I'm gonna answer your message. So again, I say I'm sorry that I didn't respond to you, Ugam, but I will respond to you after the class. Is that fine?
Yes, that's
Yeah.
okay.
Okay, sure. Thanks. Yeah, feel free to message me either publicly in the Teams channel or privately. I will be responsive. So that's one thing. Is there any question about the course, assignment, anything before we start? Any ambiguity? Everything is clear?
Hi, Ben. Hi.
Hi.
I actually wanted to know that if you're doing the calculation for the question using some two different methods, can we have like two different optimization answers, or it needs to be the same?
So if the optimization problem is a convex optimization problem, then whatever you use, you will have the same problem. So if it is a strongly convex, you will have the same optimization variable and the same, I mean, you will have the same optimum optimization variable and you will have the same optimum optimization function, right? If it is a strongly convex.
Okay, okay.
If the optimization problem is convex, so it means that the objective function is convex and the constraints are also convex. You might using different methods, you might find different optimum optimization variables, right? Because this might be like this, with where all of them have the same optimization optimization function. Let me share a screen so I draw
Okay.
and you can see. Just give me a second. Okay, so what I mean is this. So if the cost function is a strongly convex, then you will have one argmin or argmax, doesn't matter, and one f of x star and one x star, whatever optimization problem that you use. If optimization this is, you have a convex optimization problem and your cost is convex, not necessarily strongly convex, it means that you might have, in this case, you might have different x stars, right?
Okay.
But they have the same f of x star. So you will definitely find, using different algorithms, you will find the same optimum optimization function. However, your optimum optimization variables might be a bit different if this case happens. But if it is convex and the cost is like this, you will still have one x star, right? So that's one thing you should note. And also, if the optimization problem is not convex, so something like this, right? So you might, using different optimization algorithms, you might find different local optimums. And that also will depend on the initial point. So assume that, for example, we will see soon we will see gradient descent and those methods. For example, you will start from here. It depends both on the algorithm and the initial point. And you will start here. So if you start from here, you might end up here and you find x star. If you start from here, you might end up here. So if the optimization problem is not convex, you might not necessarily, it doesn't guarantee you that you will find the same solution using different algorithms, different initial points. And also, as I said here, initial point matters, right? Therefore, that's why when the objective function is not necessarily convex, people, in order to find the same solution every time, they usually set the random seed in their code. So every time they start from the same initial point, and they will end up with to the same local minimum. You get my point? So setting the initial random point, yes, random seed in your code means that you will start from the same initial point. So that's one thing. Any other question?
Thank you. Thank you, man.
No problem. Any other question? Is everything clear? Okay. So before we start, I wanted to add 2 points to tell you before we start. Is that one thing that, do you remember for linear programming, we were talking about dual problem, and I said this, that about the duality, strong duality and weak duality. I said the gap is non-negative. It's either 0, which means strong duality, or positive, which means weak duality. And I showed using these functions, right? F and G. F was the primal problem, G was the dual problem. What I meant here, I didn't mean that the cost is, it was just for general understanding of duality, strong duality and weak duality. I didn't mean that the cost is quadratic, right? So please don't be confused. I'm completely aware. You should also note that this is a linear programming. If we are talking about linear programming, the cost is also affine or linear. So it means that if, for example, we are minimizing, assume that the cost is going down like this, and based on the constraints, the solution might be here, right? And if in linear programming I'm talking, the cost is linear, G is going up, for example, and according to the constraints, this optimum is here. So the gap is this. So I didn't want you to be confused by why these are quadratic. I was only talking about duality, not necessarily in linear programming. If it is linear programming, then the case is like this, something like that. So the cost is linear. That's one point that you should note. Another thing that I wanted to tell you before going and continuing the course is about the integer linear programming. I remember one of you guys said that one thing we can do for integer programming is that we solve the continuous optimization, and then at the end we round the solution to an integer or to the discrete value in the discrete feasible set. However, I said, yeah, it's kind of relaxation. However, you should note that if we want to do that exactly, that's not necessarily true. I can show you with the counter example. Specifically, for example, in integer linear programming, let's talk about that. Let me add a page here. So, assume that these are the feasibility points which are integer, right? And so let me think.
No.
So please turn off, if you have question, turn on your mic, otherwise turn it off, please. So let me think. Yes, something like that. Assume these are the constraints, right? And so if it was a continuous linear programming, the constraints were like this. Right? The intersection of the constraints, and the solution, for example, would be, just give me a second. I want to show you some example. No, I think it's good to have it like this. Assume the points are like this. So these are the integer points. Okay. Yeah, I think this is a good example. So assume that the cost was in a way that this extreme point was the solution of the linear programming. So this gives us x star, x1 star, and x2 star, x1, x2, and the cost was been increasing in this direction, something like that, right? What happens if we do what you said? So let's solve this linear programming, and at the end, let's round it to the nearest integer. So this is the extreme point that is found by the linear programming, and if we round it to the closest integer, it will be here. However, this is not in the feasibility set, right? This is not in the feasible set. The feasible points, discrete points, are only these that I'm bolding, making them bold. Only these, and also the points on 0, right? These are only the feasibility set. So rounding to the closest integer is not necessarily the correct thing. That's why we do the branch and bound. if what you said was correct, we could do it in one shot. We just solve linear programming and then round the solution to the closest integer. But this is a counterexample. We can't do that. That's why we do branch and bound. And using branch and bound, we make the feasibility set smaller and smaller until we end up with solutions which are integer. It means that the feasibility set becomes in a way that the extreme point, which is the solution, falls on an integer solution on one of these points. So this is it clear? Yes, can you give me any feedback, please?
No, can you explain it again, please?
So it means I'm saying that one of you said that for solving integer linear programming, let's relax it to linear programming, solve the linear programming, and then round the solution of the linear programming to the closest integer. For example, this point, this x star is, let me think. So yes, I think 1.8, and this is 1, 2, 3, 4, 4.8, something like that. Okay. So assume that we solve it, and this is 4.8 and 1.8. And he said, let's round it to closest integer, which is 5.2. And what is the closest integer? Which this is 5.2, right? However, this is not correct. This is a counterexample. 5 and 2 is not in the feasibility set. What is the feasibility set for the integer linear programming in this case? Are these bold points, right? This is not in the feasibility set. That's why we are doing branch and bound. We can't just do it in one shot. We need several shots of linear programming. We're using branch and bound. We make the feasibility set smaller and smaller until, interestingly, an extreme point falls on a one integer solution. So the feasibility set becomes smaller and smaller. That one of the extreme points is integer then, and that extreme point is the optimal extreme point. That was a counterexample for just rounding to the closest integer. Clear? Okay. Great. So that's the philosophy behind integer linear programming. Now let's continue with the sensitivity analysis. Okay. So where were we? Yes.
I have a question about this session before the previous session, the bigger method. Can I ask it now?
Yeah, sure.
Can you go to page 35 of I think 35 of 59.
Yes.
In the first constraint, R2 minus E2 is correct, yeah?
You're right. Thank you. Thank you for correcting that. You're right. Yes.
Thank you. I was
Sorry
confusing.
about this
And
type.
can you go to 55, page 55?
By the way, you know the reason why it's minus, right? Because A minus E can become negative.
Yes.
I showed you a technique. This is a technique. When your variable, this technique can be used for also negative optimization variables in linear programming, because as you remember, in linear programming we assume that optimization variables are non-negative, right?
Exactly.
What if it is negative? We can replace that optimization variable with two other optimization variables, x plus minus x minus, something like that. And by playing around with these values, then the solution might be negative. For example, minus 30 can be written as 50 minus 80. 50 and 80 are positive, but 50 minus 80 becomes negative, which is minus 30. So that's the technique that we were talking about. And what was your question again? The the next question.
Thank you for your response. And can you go to page 55?
Let me bring it. Yes. Okay. I
In the
can't hear.
table, the first row, R1 minus R2, I think is wrong because the pivot row is R4. Yeah.
Just give me a second. Let me think. So this is let me think. So
In the table below the first
yeah.
row, you wrote R1 minus R2
This is R1 plus
plus
R4
R2 divided
R4
to
R4
R4.
divided.
Yeah.
And but these numbers are correct, I assume. These are correct. So 2 minus half is 1.5. So 1 minus 1 is 0. 1, yeah, I think you're right. Thank you. That was a typo here. So but the table is correct, right?
Thank you very much.
Yeah, thank you. Thank you for letting us know about these typos. I will fix them and I will re-upload them. Thank you. Any other question? No? Okay. Thanks. So let's go to sensitivity analysis and finish that. And then we'll go to KKT conditions. So let's recap what we had for changes very, very quickly. So after we found the matrices and we defined the matrices and vectors, I'm not gonna go into that again. We covered some cases of change. And so what was the idea behind sensitivity analysis? It was saying that how much sensitive our optimization problem, in this case linear programming, is to a change, some change, or a combination of changes in the optimization problem. And this change can be, for example, the coefficient of a variable, either basic or non-basic, in the objective function. It can be a change of coefficient of a basic or non-basic variable in the constraints. It can be adding a new variable. It can be adding a new constraint. It can be a combination of changes, different changes that we can have, right? So case 1.1, for example, here we have an example. We are changing, this is optimization problem. We want to change the factor of x2 from 30 to either 32, 36, and see what's the difference. For example, an example is that your manager comes to you and says that the investors want us to change the profit of the second product to $32 or something like that. Some change imposed by industry, by manager, by the constraints, whatever, some restriction. And the manager asks you, do you recommend this change? What happens? Should we change the line of the company, the factory? Should we produce it X2 still, or should we stop producing that? What should we do? And as the engineer, you need to know what to do. Okay, so you assume that you already have solved this optimization problem in your documents, so you know that here X2 is a non-basic variable. So you knew that so far the factory was not, or the company was not producing the second product at all because its optimal solution was 0. But now the company is increasing its benefit. Let's see what happens. So we already have these because we already have solved them. We assume that we have solved them, and we know that, okay, what is 30? It is the factor of x2. It means that it is C2, right? And it is a non-basic variable. X2 is here. It's a non-basic variable. Therefore, we are changing this element of Cn, and in this table we should see where does Cn have effect. So here we have it, we have some effect, and let's recalculate it. So CB transpose B inverse, we already had B inverse, but we get the column of x2 because we're talking about x2 right now. We don't need to calculate for other columns. And this is CB, it doesn't change, but we need to have it here, and CX2. So let's make it parametrically, and we say 30 plus some delta, and it becomes 5 minus delta. This should be non-negative, and therefore delta should be less than 5. It means that we can, if we increase the profit of x2 to 35, still nothing changes. The company doesn't need to produce x2, and the optimum solution is the same as before. However, if we increase it to, for example, 36, which is more than 35, it means that we need to continue the table. So in sensitivity analysis, we need to check whether we need to continue the table in order to update the optimal solution or not. Here we are saying that, okay, this is changed to -1, because if you recalculate that, you will see that it becomes -1. And the rest of the table doesn't change. So we do row-wise elementary calculations again, and we will see after one step this row, the C row, becomes all non-negative, and then we'll see that the cost has improved because the benefit we have increased the profit of x2, and also the basic variables now are S1, X3, and X2. What were the basic variables before? They were S1, X3, and X1. Now it means that by increasing the profit of X2 to 36, X1 isn't a basic variable anymore. It becomes non-basic. Therefore, the company needs to stop producing X1 because its optimal becomes 0 now, and start producing X2 because it has become a basic variable now. So this is the idea. Now, case 1, 2, an example. So now let's change the factor of a basic variable in the objective optimization function and objective function, and let's see what. So we can calculate now. CB has changed, and what are we changing? We are changing 60. So for x1, the factor of x1, so it means that we're changing here. Now CB has changed. In this table we see that this is changing, and also this part is changing. So the cost is also changing. We need to recalculate both of them. So let's recalculate these parametrically, and then we can find the delta, the condition of delta for not having any change in the optimization. We'll see that if CX1 is changed from 56 to 80, nothing changes. But if we have a drastic change, which is beyond this interval, then we need to recalculate and continue the table. In such cases, we need to calculate both of these parts where the table has changed, and then we'll see that in the updated 0, not only has this changed, but also we have change in the cost, right? And then we do we continue the table. We choose the pivot column, pivot row, mean test, and then pivot row, and do the elementary row-wise calculations. We do it until we reach the termination condition, which is all non-negative values in the 0. And then we'll see, okay, now the basic variables are S1, X3, and X2. So X1 now is not a basic variable anymore here. And the cost also has changed, and it has been decreased. So you will say to the manager, if you apply this change, our total benefit, our total profit or whatever comes to the company is decreased. However, if you insist to do that, you need to stop producing X1 and start producing X2, something like that, right? So case 2.1 of change is a change in a coefficient of a non-basic variable in the constraint. So it's now Aij, not C anymore. So an example here is that now this example is an example of a combination of changes. So here in this example, we are changing both coefficient of x2 in the objective function and also the coefficient of x2. Yes, coefficient of x2 in the constraints. So here we are changing this 6 to 5. We are changing this 1.5 to 4. 2 is the same, and the rest of the factors are the same. We are also changing this 30 to 50. What happens? We should see, okay, where do we have C2? So as x2 was x2 in the basic variables? Let me, because I don't remember, I need to check. x2 was a non-basic variable. So it means that in Cn, it is in Cn, right? Cn. We should see where in the table we have Cn. We also should see where in the table we have, so Aij of x2 has changed, and as x2 was a non-basic variable, it belongs to n. So wherever we have n and Cn in the table, we should see we should recalculate that either parametrically or using the numbers that we have and see whether we need to continue the table or not. So that's the thing, the idea. And any questions so far? Everything is clear?
Yeah,
Right.
everything's clear.
Okay, great. So for example, in this case, we are changing, so x2 is a non-basic variable. We have these changes, and so here, so this has become 50. It was 30 before, now it has become 50. And we also have Cn and n here, therefore we need to recalculate this here. And you will see that in this case, it is non-negative, so we don't need to continue the table. It means that manager, we can do what we were doing as before. Okay, case 2.2 of the change. What is it? It's a change of in a coefficient of a basic variable in the constraints. So in the previous example, it was a change of a coefficient of a non-basic. Now, what if we change a coefficient of a constraint in a basic variable? So we'll have, for example, in this case, we're changing 8 to 5. We're changing 4 to 5. We're changing 2 to 1. And we are asking what happens. So it means that, and this Aij is in B because x1 was a basic variable. So we should see in the table, we should calculate that term, this term again, and see if it all terms are non-negative or not. If yes, we need to continue. We might have a combination of cases too. We might have, for example, what if we change 8 here and 2 here? So we have change in both B and N, right? So these are the cases you need to see where in the table we need to continue the table or not. So for example, here we're changing these. So these are changed in B. And if we recalculate that, so see, this has been changed to this. And we need to calculate this inverse again. And if we solve that, if any values become negative, then we should continue the table. Otherwise, the total profit does not change. And by the way, you can use calculator in your exam for calculating inverse of matrices. Don't worry about that. Okay, so case 3 of change. Please feel free to interrupt if you have any question. Adding a new variable to optimization. So now I think until here we talked about it in the previous session. Now it's new. Adding a new variable to optimization. It means that assume one optimization variable has been added. So if we have, for example, 2 variables, it becomes 3 variables, something like that. It means that the managers, for example, says that I want to have another product. I want to add another product to the line of production. What happens with this profit? So we need to check that. So, for example, here 60-30-20 as before, and the company is adding a new product X4 with a profit of $15 or $25, and the constraint is this. It means that in these 3 constraints, we will add plus one X4 plus to this. Also, we'll have plus 1 X4 to this. We also have plus 1 X4 and see what happens. And we'll have 1 X4 here also, which is greater than or equal to 0. We'll have 1 X4 here as the optimization variable. What is your recommendation to the manager? Let's see, for example, here. So by the way, when we are adding an optimization variable, we should assume that it's a non-basic variable, right? Because we don't know, we don't have the optimal value for that. We assume that it's a non-basic variable. We are assuming that let it be 0. Let the company not produce that and see what happens. So that's why we can say, okay, in the n I will have an additional column for AX4 and see what happens. So C B transpose B inverse is as before. This is B inverse. And this is CB transpose as before. Now we are adding this column in N. I'm not calculating for other columns in N as before because we don't need them right now. This AX4 doesn't affect the other columns in N. So, and also CX4, we need to consider that the profit of X4 in the cost as here we have here, right? So we have this because its profit was 15 and it becomes 5 here. It means that it's non-negative and we don't need to, it doesn't change the total profit, and we can say, manager, we don't need to produce that. But if you change the profit, then you may need to, the manager might have a follow-up question. Okay, what should the profit of the additional product be at least that we start producing that, and it changes our profit? Then you can solve it parametrically, right? And see, okay, 6, assume you can make it delta or whatever, and then solve for the delta. And you will say, or what the manager might have another question. I want the profit of the X4 to be the same as 15 that I told you. However, I changed its factor or factors in the constraints. I changed the restriction on that. What happens? Then you can also put the parameters here. Delta 1, delta 2, delta 3, whatever. And then solve parametrically and see what happens. And you can report to the manager. Manager, if you do this, if you put this at least in this number, then you can start producing that, but I need to recalculate and continue the table to see what will be the production. For example, I guess if it becomes a negative, and if you calculate that, this is my conjecture, then X4, which has been newly added, becomes a basic variable, and it kicks out one of the already basic variables to become non-basic. So X4 becomes a basic variable, and one of the already basic variables becomes non-basic. It means that manager, okay, if you do that, then you need to stop producing the other product, but you can start producing X4. By the way, you might be wondering why adding a new variable always either doesn't change or kicks out another product. Can someone tell me why? So in this problem, in this optimization problem that we are looking at, right? Assume that we have these and I add X4. It either doesn't require me to produce X4, or it comes to the line of production but kicks out one of the variables. Can you answer me why this is happening? Please let me know your thoughts. It might be wrong. That doesn't matter. We are brainstorming. Did you understand the question, or should I repeat it?
If you could just repeat it, I didn't quite like
Yeah.
you're saying
So
to add X4, so we're adding another product.
yes. So we are talking about the case where we are adding a new variable, right? A new product, X4, right? I'm saying that when you are adding a new optimization variable, X4, in this optimization, it either you will end up that X4 becomes a non-basic variable. So it means that its X4 star becomes 0. It means that you don't need to produce X4 at all. So then you will tell the manager, you want to produce that, but you shouldn't because it doesn't change the total profit. Or X4 becomes a basic variable, but kicks out one of the already basic variables. What were the basic variables? So what were the basic variables? Let me review. So the basic variables were S1, X3, X1. S1, X3, X1. Let me write it down not to forget. S1, X3, X1. By the way, note that one of the basic variables might be a slack variable, right? So it means that it might replace S1, then still you were not producing S1. S1 was a slack variable. So you were producing, for example, before you were producing X3, the third product, the first product, but you were not producing the second product, and a slack variable was some non-negative. The first slack variable was some non-negative value. However, I'm saying that, I'm claiming that when you are introducing adding X4, either it doesn't need to be produced at all, or if you add that and it needs to be produced, it will replace one of these. Either S1, if it replaces S1, it means that in addition to production of X1 and X3, you need to produce X4, or it will replace one of these. It means that you need to stop producing the first or third product and replace it with the production of X4. Why is it correct? Why is my claim correct?
Well, when you do the simplex method, you only have 3 basic variables, so it has to knock one of them out. So if it knocks S1 out, then you're adding that product, like you have to produce an additional product, or it has to knock X1 or X3 out. So then you'd basically say stop producing X3, start producing X4. So you're only allowed, based on that method, you can only, there's 3 basic variables, so you have
three only
to
basic variables.
replace
Yeah.
one of them.
Exactly. Yeah, exactly. What you said was correct. But my follow-up question is that why do you have only 3 basic variables in this problem?
Because we have 3 products.
Not necessarily, no. We have 3 optimization variables before introducing the slacks. I agree.
Yeah.
But it doesn't necessarily imply that you will have 3 basic variables.
Okay.
Why do you have 3 rows excluding the 0 in your Tableau method here?
That's how many constraints there are in the problem.
Exactly. It's because of the number of constraints excluding the default constraint. Excluding this default constraint, you have 3 constraints. If you had 4 constraints, although assume that in the same problem, although you had 3 before introducing stack variables, assume you had x1, x2, and x3 as 3 optimization variables. But you had 4 constraints excluding the default constraints. By default constraint, I mean this. Excluding these, assume you had 4 constraints with 3 optimization variables, x1, x2, x3. You would have
To introduce
4
X4
rows.
compulsory.
No. Don't confuse with the x4. So assume that, compare these 2 problems. Subject to, I want you to understand what's going on in Tableau method. So let me replace the inequalities with the slack variables right now. I'm copying and pasting the same thing here, the same thing here. And some, let me write down the default constraint of a standard linear programming problem. So up to now, so far, it's exactly these two are exactly the same, right? However, I'm gonna add a 4th constraint. Assume whatever. It might not have any x3, 0 x3, whatever. And I will have a slack variable for that too, right? And if it is greater than or equal to, then I would have additional or an excess variables. So the only difference is adding this constraint. It means that we have 4, excluding the default constraint, we have 4 constraints. It means that when you, so comparing this, when you make the Tableau method for this, you will have 4 rows and the 0. When you are making the Tableau method for this, you will have 3 rows and the 0. Although they both have x1, x2, and x3 as the actual optimization variables before introducing the slack variables, right? So the number of rows in the Tableau method does not necessarily depend on the number of optimization variables. It depends on the number of constraints. All right? Is what I'm saying correct?
Yeah, that makes sense.
Okay, so, and we know that eventually the number of basic variables are exactly the number of rows in the Tableau method, excluding the 0, right? So it means that whatever number of constraints we have, that number of basic variables will end up with, right? Is that clear?
Yeah.
Okay, so having a constraint will have several impacts. In addition to introducing a new slack variable or additional and excess variables, in addition to that, it will also add the number of basic variables, the count of basic variables. So that's the thing. And that's exactly, so this was a follow-up question to my previous question, which was answered by you. So you said that my first question was in this, so one of you said that the number, you were confusing this question, my follow-up question, with x4. In my follow-up question, it doesn't care whether it's for, we have x4 or not. So my first question was, my first question was, in this problem, optimization problem, if we add x4, it will kick one of these out, either kick one of these out, or it becomes a non-basic variable. And it's why you answered because we only have 3 basic variables. My follow-up question was, why do we have 3 basic variables in this problem? Because we have 3 constraints excluding the default constraints, right? And please note that this is not 1 default constraint. This is actually 6 default constraints. So we have x1 greater than or equal to 0, x2 greater than or equal to 0. We are just writing them in 1 line to be short, okay? Excluding the default constraints, we have 3 constraints. It means that we have 3 basic variables. But if we had this problem and we were introducing x4, what would happen? So we knew that we would have 4 basic variables, and then the answer to the first question would be this: either x4 becomes a non-basic variable, so we don't need to produce that, or it will kick out one of these 4 basic variables. Some of them might be slack variables. Some of them might be actual variables. So that's the thing. Did you get the story? Is everything clear?
Yeah.
Okay, great. So now I think you understood Tableau method better. Okay, so here an example, x4 is a non-basic variable. So I think once we here in this case we have 15, in other case we have 25, and we're seeing if we have 25 as a factor in the factor of x4 in the cost, then it would become negative and we need to continue the table. That's the thing. So here, for example, if that's the case, the cost, the 0 is updated and we have -5 here. Therefore, we have a negative value in the 0. We choose a pivot column and then mean test, pivot row, elementary row wise calculations, and these are updated. So here, that was an example. x4 has kicked out x1. Now x1 has become a non-basic variable and x4 has become a basic variable. And why do we have 3 basic variables? Because we have 3 rows here, and it's implied by this 3 constraints excluding the default constraints. Okay, case 4 is that adding a new constraint to optimization, right? Okay, this can have 3 subcases, sorry. So 4.1, 4.2, and 4.3. So 4.1, assume that the current optimal solution. So we have a current optimal solution so far, right? Now we are adding a new constraint. For example, in that case, we had 3. Now we are adding a 4th constraint. Doesn't matter, whatever. Either our current optimal solution with the previous constraints and all of them satisfies the new constraint, or our current optimal solution doesn't satisfy the new constraint. However, linear programming still has a feasible solution. And what does it mean? That its feasibility set is non-empty. Or it doesn't satisfy, and also it doesn't have a feasible solution. It means that adding the new constraint makes the feasibility set empty. And when does it happen? It means that, do you remember we said whenever our constraints are contradictory, our feasibility set becomes empty and we don't have any solution. It means that adding this new constraint has been contradictory to our previous intersection of constraints. So when that's the case, it means that the feasibility set becomes empty. Let's see some examples. For example, here, assume that this was a previous feasibility set. So this is a previous feasibility set right here. So these were the default constraints, and these 2 are the constraints. We had 2 constraints, and now we are adding a 3rd constraint, like this. In the first case, our previous solution satisfies this constraint. So that's fine. So it means that we don't need to continue, right? Because this is satisfying. And by the way, and in this case, this, for example, here it is making the feasibility set smaller, and also the previous solution, which was here, is not satisfying the constraint, the additional constraint anymore. Now the solution has changed. In the third case, assume that it's saying that it should be in this case, and then it means that the intersection of the constraints altogether is empty. So it has become a non-feasible problem. Okay, a question. Can adding constraint, this is a good question. Can adding a constraint improve the optimal value of the objective function? I mean, f of x star, I mean c star, right? When we are adding a constraint, can it improve the c star? So if we are if we have a maximization linear programming, it means that does it increase c star? If we have minimization linear programming, does it decrease c star? Can you please answer me?
I mean, just off the top of my head, like looking at the graphs, I would say no. It wouldn't improve.
And can you say why? I think intuitively it's obvious, right? The reason is that when we are adding a new constraint, we are making the feasibility set smaller. So it means that we are having more restriction. With less restriction, we have more freedom to increase the cost function, or if we have maximization. Now we are adding a new constraint. It either makes the solution as before, or it makes it worse because we are adding a new constraint. So we had the same thing in integer linear programming when we had the branch and bound. See, when we are making the feasibility set smaller and smaller, we are making it worse. We are making it worse. Why? Because if, for example, consider the extreme case where we have a linear programming optimization problem with no constraint. Assume maximize x1 and x2, 3x1 plus 4x2. What is the solution? With no constraint, x1 star, x2 star infinite, and c star would be infinite. When you are adding a new constraint, you are restricting that, then the solution is not, c star won't be infinite anymore. It will be less because of your added constraint. So the more constraints you're adding, you're more restricting the cost more and more. So this is the case.
In theory,
Yes.
I just had a thought. In theory, it doesn't necessarily have to make it worse. It could also be equal. It could be equal
Yes.
or worse, because
Yes,
the new constraint could also go through the existing vertex, or what do we call that? Yeah, vertex.
Yes, exactly. Or even not necessarily passing through the vertex. If as long as the solution is satisfied by the, like this case, by the new constraint, then that's the case again. You know. So you're right.
Yeah,
It's
true.
either the same solution or worse, right? Here is the same. Here is worse. Assume that the cost is going like this. Right? Is that obvious?
Yeah.
Okay, so that was a good thing to note. So case 4.1, let's go through them fast. I think it's not very hard. Example, the company has profit 60, 30, 20, the same as before. Let's see what is happening. Okay, we signed table, the table that we had, the slide 8. The solution was this. The company is adding, so here it means that x1 star and x3 star were basic variables, and x2 was a non-basic variable. The company is adding a new resource constraint like this, adding a new constraint. And let's see. Okay, it's been satisfied by the new constraint. Therefore, so we are putting x1 star plus x2 star plus x3 star. It becomes 10, which is less than or equal to 11. It means that it's satisfied, so we don't need to continue the table. So it means that the manager says, okay, I'm adding this restriction, and this restriction is applied by investors. I can't do anything about it. So in industry, usually when the investor wants something, it must happen. It must happen because they are paying. So you say, and the manager says, oh, please let me know whether I need to change anything to the factor or not. Okay, you say, okay, no, it already satisfies our optimal solution, already satisfies the new constraints. So you don't need to worry, manager. So this is what happens. Okay. Now let's go to case 4.2. We saw in the table that the solution is this. The company is adding this. The investors want to add this new constraint. It means that something, the product, they say, okay, for example, so it means that our optimal solution was saying that we are not producing any X2. And the second product was not being produced by the company. However, the investor says, no, I want the company to produce at least one scale, and this one might be 1 kilogram, only one, or whatever, 1 meter, whatever. One scale of this second product, because I like that. You need to produce that. Although it's not optimal, you need to produce that. Then we have to listen to the investor. So let's add that to the optimization problem and see what happens. So a new constraint has been added. Okay, now a good tech. Let's use the dual simplex method. Do you remember? Let's convert this to less than or equal to. If the constraint was already less than or equal to, we didn't need to do that. But as it is greater than or equal to, let's do this. Times -1, the direction of inequality is reversed. Then we can add the slack variable. Or we can do the big M method, but I think it's simpler here to use the dual simplex method. And then it's kind of like, as you remember, we're kind of working with the transpose of the matrix. Get the negative value in here, and then pivot row, and then pivot column as before. And with one step, we see that all of these become non-negative. Therefore, we can stop. Now let's see what has changed. So here, S4 was replaced by X2. Now, so X2, as the investor wanted, has become a basic variable because of this constraint. Obviously, X2, even before solving this table, we knew that X2 would become a basic variable. Why? Can you please let me know? Even before solving this, continuing this table.
You have to produce it, so it has to be a basic variable.
No, yes, why? Because the constraint says that it has to be at least 1, right? It can be 1, it can be 1.1. It's not an integer program, it's linear program, it can be float. So it's 1, 1.1, 1.3, it might be 10, it might be 20, but it must be at least 1. It means that it can't be 0. So it can't be non-basic, because non-basic means 0, right? Is it clear now?
Yeah.
So it has been forced to us that X2 should be produced. And as you see, producing X2 was not very desirable in this optimization problem. That's why. Why? Because when we solve it, we'll see X2 star has become 1. The least amount that the restriction was imposing on us. It means that investor, okay, you want X2 to be at least 1. Doesn't matter. I will produce exactly 1, because the more I increase X2, apparently my total profit doesn't like it. So if producing X2 was desirable, then of course it would become a basic variable in the first place. As the optimization problem had says, okay, it must be 0. It means that it's not very desirable to produce X2, but doesn't matter. You want it, I produce it.
Would the solution not always be the lowest value? Because if adding a constraint is always going to make your solution worse, then adding the least amount is always going to give you the maximum result. So in this case, if the investor said must be greater than or equal to 2, well, then 2 would be the optimum number for X2, or 3 or 4.
That's a good point. I'm not sure about it, but I think you're right. But you should note that this is just an example. What if the investor says, I want X2 plus X3 be greater than or equal to 1? Then you can't say that. So as the constraint is simple, then I think your analysis is correct, right? What if the constraint is complicated, like x2 plus x3 is less than 4, or x2 plus x3 is greater than 1? Then you can't simply say that. You get my point?
Yeah, I see.
Again, even with your analysis, if the constraint is simple like this, you need to continue the table to find out the optimal value, because the optimal value for other variables change. Also, you need to know which already basic variable is replaced by x2. We don't know that. You need to solve the table, continue the table to see which already basic variable is kicked out by x2, right? That's one thing. You need to solve that, because you should tell manager you need to stop producing that and start producing x2. Or if x2 kicks out a slack variable, then you say, manager, you don't need to stop producing other products, but you have to start producing x2, something like that. We have used dual simplex method here. Okay, let's go to case 4.3. So 4.2 didn't satisfy the, so what was 4.2? 4.2 didn't satisfy the new solution, but has a feasible solution. 4.3 doesn't satisfy the previous solution, and we will see that the example that we are gonna solve doesn't have a feasible solution. You will see that. So it means that case 4.3, manager says, okay, so far whatever you produce is good, but now I like x1 plus x2 be greater than or equal to 12. And you'll say, okay, let's calculate. Maybe what you want is not possible. Not necessarily whatever you want we should do. We should say whether it's feasible in industry to do that or not. Let's see. Okay, again, we multiply it by -1 and then add the slack variable and continue. Okay, here we are solving. So when we reach here, again, if recall the dual simplex method that we already discussed before. When we reach here, we'll see that, do you remember? No, we need to continue. We need to continue. We continue the dual simplex method. I'm not gonna go over the dual simplex method again, but in dual simplex method, whenever we chose the pivot row, for choosing the pivot column and doing the mean test, we were saying that divide this by the negative values of in this row. Here we reach to the point that where we don't have any negative, all of them are non-negative. So it means that we can't continue the dual simplex method. We can't continue the table. It means that we don't have any feasibility solution. We can't. It means that the newly added constraint has made the feasibility set empty. It doesn't make sense. Manager, please tell the investor we can't do that. Please either change your restriction or let us continue what we were doing, right? And then manager will have a meeting with the investor. It's not possible. It's not feasible. For example, change your restriction, and the investor says, maybe okay, let's change 12 to 8, and let's see what happens. X1 plus x2 be at least 8. Does it solve the issue or not? Or let me change the constraint completely. Let x1 plus x3 be at least something or less than something, and let's see. So then it will be a back and forth meeting between manager and investor and the engineer of the company, something like that. Anything? So the lectures are inspired by Professor Shukuf Mirzai on sensitivity analysis. I have put the link here. I'll also put the link in the description of the YouTube video. So sensitivity analysis in linear programming is over. Is there any question before we move to the next topic? Everything clear?
Yeah.
Okay, great. So let's have a break now, I think, because we are going to change gear a bit and continue with KKT condition after the break. let's come back in. Okay, right. Let's round it up. 8:30, right? 8:30. Let's come back and then we'll continue with the KKT condition. Okay. Thank you.
Ben, I had
Yes.
a quick question if you're just
Yeah.
free during this.
Yeah, sure.
So I guess this relates just to the wording on the assignment, but also there was a very similar question in one of the lectures. So one of the question, basically, you have a cost function, and it said
Okay.
there's $3 profit for X1, $2 profit for X2.
Sorry, which
And
question
then
are you talking about? Sorry, which question?
let me just bring it up. Just give me 1 second. I can bring up we might as well go off of the actual. Okay, assignment 1. I'm just opening it here. So this is for question 2. So
Okay.
you form your cost function, and I won't go into detail so I don't give anything away for anyone. But then it said to form the actual constraints, the resources for 2 of the first product and 1 of the second product is at most $9. Now, I'm confused about this because this would be like 2x1 plus 1x2, and then which the resources for the second are at most, so less than or equal to 9.
Yes.
Now, if it's like you have 2 of x1, but x1 is also a unit, how many units? So you're like, you have units times units plus units times units is less than or equal to a dollar value. It conceptually doesn't make sense. Do you see what I'm saying?
Yeah.
Like, if you change the question that it's $2 and $1, then it conceptually makes sense. Do you see what I'm saying?
Yes, exactly. What I meant was this. Maybe, yeah, the rewarding should be improved here. You're right. So we should say that per the first product, if we have $2, and per the second product, if we have $1, it should be at most $9, something like that. You're right.
Yes.
Is that correct? Yeah.
I
So that
just
we have
wanted to make
compatibility of units in the equation, you mean, in the left-hand side and right-hand side. Yes, I agree.
I just wanted to make sure that it was the case.
Yeah, you're right. This also, what you're saying is also important in physics, because in physics units are very important. The left-hand side should have the same unit in the right-hand side. Even you can find some equations in physics, or derive some equations based on just compatibility of units. In physics, many people do that. You can even, I remember I was looking at a YouTube video. It was talking about one of the Hawking's very famous equations for radiation of the black holes, and using the compatibility of units, although it's complicated, but he derived the equation, and it was very cool. So you can derive very complicated equations in physics using compatibility of units in left-hand side and right-hand side. Yes, you're right.
Absolutely. Yeah, no, I wanted to make sure. I mean, it's still solvable. Like if you ignore that, it's I went through, I solved it, no issues or anything, but I just wanted to make sure and run that by you.
Yeah, you're right. Sorry about it. Yes, I think I need to have a better wording for the questions. Yes.
No worries.
Okay.
All right, I'm gonna grab a drink, but
Yeah, sure.
I'll jump back online in a couple minutes.
Okay, sure. Great. So
Right,
see
thanks,
you
man.
at 8:30. Sure. Thank you.
Sounds good. Thanks.
Thanks. Great. Thank you. Okay. Now we shift a little bit of gear. Now our gear changes toward KKT conditions. So far we were after preliminaries, we were focusing on linear programming, integer linear programming, sensitivity analysis, and these things. Now we are gonna go to KKT conditions. And after KKT conditions, we are gonna talk about the first order methods and etc. Okay, so first off, please note that KKT conditions are the backbone of optimization algorithms, and many of them kind of use either directly or indirectly the KKT conditions, and you'll see that why they are very important. There are important conditions in optimization. Many of optimization algorithms use these. Okay, just give me a sec. Yes, so many of the optimization algorithms use KKT conditions. Now let's start with the Lagrangian function. You'll see that the Lagrangian function is very important in optimization. I think I can say it's the most important function in optimization. Okay, let's see what, of course, it's named after Lagrange, who was a great mathematician. Okay, so please feel free to interrupt and ask me if there's any ambiguity or question. Consider this optimization problem where we are f of x is the objective function, x is the objective variable here, and we have the inequality constraints m1 inequality constraints. So what does it mean? It means y1 x is less than or equal to 0, y2 x is less than or equal to 0 until ym1 x is less than or equal to 0. So we have m1 inequality constraints and m2 equality constraints. h1 x equals to 0 until hm2 x equals to 0. So we have in total m1 plus m2 constraints, right? And why can we write all inequality constraints like this? We'll show. So if we, for inequality constraints, so constraints are either inequality or equality, right? For inequality constraints, we have either less than or equal to or greater than or equal to. If it's already less than or equal to, it's like this. By the way, what do I mean by y1x? It's a function of x called y1. It can be, for example, this can be, it's not now, henceforth, it's not necessarily linear. So far, what we learned, the constants were linear. Now it might be non-linear. x2 plus 3x less than is x less than or equal to 1. And if x is a vector, it can be the elements on the element. The constraint might be on the elements. x1 squared plus 3x2 is less than 0 or something like. y2 might be a tangent function. Tangent of x is less than 0, whatever. So right, and h also is a function. So h1 of x might be x3 plus 2x, something like that. Whatever function is it we have. So it's in general, and it's the inequality constraints can be either less than or equal to or greater than or equal to, right? If it is greater than or equal to, we can simply change it to a less than or equal to constraint by multiplying by -1. It becomes less than or equal to, and now rename minus k to y. So you can rename that, right? So y ix, define it to be minus k ix, something like that. Here we have it. So assume we have x1 plus 3 x1 squared plus 3x2 is less than or equal to, and x1 3 minus 2x1 is greater than or equal to 0, whatever we have. For these greater than or equal to it, they might be several of them. For each of them, we just multiply them by -1. So we can write all of the inequality constraints to be less than or equal to. And if we have a maximum, so here we assume that it's minimization. We can have a maximization problem. If it is a maximization problem, we already discussed it. We can say it's equivalent to minimize of minus f of x. So when if we are maximizing f, we are maximizing f. If we multiply it by -1, the f, sorry. So minus f is this. Now we are minimizing minus f. So their arguments will be the same, but their optimal function, objective function, will be negative of the other one, right? So we can simply define g of x to be equal to minus f of x and then minimize g of x, something like that. So in general, we can write all optimization problems in this format. Minimize of f of x, even if it is maximization, we can convert it to minimization. All the inequality constants, we can convert them to less than or equal to 0. And all the equality constants, we can convert them to equal to 0. By the way, why do we have 0 on the right-hand side? Because whatever we have in the right-hand side, we can bring it to the left-hand side. So we'll end up with 0 at the right-hand side. For example, x3 plus 2x2 is less than or equal to 1. We bring 1 to the other side. So x13 plus 2x2 minus 1 is less than or equal to 0. So that's why this is a general case of optimization problem. Right? Okay. Now, some examples for fi of x. For example, this in vector form. So this is a quadratic form, right? Or we can do it in element-wise. x1, if, for example, we have 3 variables, x1 cubed minus 4x2 minus 2x3 squared, something like that, or tangent, sine, something like that. For these, we can have either in the vector form or in element-wise form, whatever. For also these, we can have vector form, element-wise form. They can all be the same. So let's go to the next. Now we want to define Lagrangian function. This optimization problem that we discussed, which is general, the Lagrangian function for this optimization problem is this. So it comes from d times m1 times m2. Why? So d is because of the x. So assume that x is a d-dimensional vector, right? Assume that. And we have m1 inequality constraints, we have m2 equality constraints. So this comes from here, this comes from here. So it means that we have x in as the input of the Lagrangian function. We have x, we have some variables for the inequality constraints, and we have some variables for the equality constraints. We'll discuss that, okay? That's why this is what it means. But its output, the Lagrangian function output, is a scalar. So it takes some vectors, but it outputs scalars. By the way, if the optimization variable is a matrix, so here I assume it's a vector. If it's a matrix, then these the inputs of the Lagrange, sorry, the inputs of the Lagrangian would be matrix. Here we are assuming that they are vectors. Okay, now what is this? The Lagrangian says, okay, put the objective function here. Also, have the summation over all of the inequality constraints. These are the functions of the left-hand side of the inequality constraints where they are less than or equal to, and multiply each of them. So y1x with lambda 1, y2x with lambda 2. So, with a lambda, a corresponding lambda, let's call it lambda. It's just a naming. You can call it anything. What we usually by convention call it lambda, whatever. So the multiply y1 with lambda 1, y2 with lambda 2, and sum them. Sum over all of them. This is the second term in the Lagrangian. The third term is plus, do the same for equality constraints. So consider some variables nu1, nu2 until nu m2, and multiply to the left-hand side of the equality constraints where the right-hand side is 0, and then sum over all of them. Then you have plus between these, right? You can also write it in the vector form. So this can be written as a inner product. If you assume that lambda is this vector and one-dimensional vector, and nu is this m2-dimensional vector, so we have lambda 1 to lambda m1 and put them in a column vector. Nu1 to nu m2, each nu1 to nu m2 is a scalar. Each of these is also a scalar. You're putting them together to become a vector. That's why these are bold, right? M2-dimensional vector. If you write it in this way, you can write this in the vector form. Why? You are also assume that you put y1 to ym1 in a vector to become an m1-dimensional vector. Note that here we are assuming y1 output of yix is a scalar, output of hix is a scalar. That's why we put these scalars together and it becomes a vector. We can also put these together and it becomes a vector. So you can write them in this, write this also in this vector form. Either this scalar form or this vector form, we can write it. So this is this is a Lagrangian function. This is called the Lagrangian, and usually it's written by fancy L. This is fancy L, right? For Lagrangian, start of L, Lagrange. And these variables that we introduced, lambda and nu, are called Lagrange multipliers. So they have two names, either Lagrange multipliers or dual variables. They are used interchangeably. Okay, Lagrange multipliers or dual variables. And they are for inequality and equality constraints. Inequality and equality constraints. So the dual variables or Lagrange multipliers are corresponding to the constraints, either equality or inequality. It also has the objective function inside of it as a term of it. This writing this Lagrangian function is also sometimes called in the literature, it's called Lagrange relaxation of optimization 1. So if you want, so you have this optimization problem where you have objective function with some constraints, you can have a Lagrange relaxation to write the Lagrangian function in this way. So you're putting the constraints next to the objective function by summing them. We'll talk about it in a few slides. And this is also called Lagrange relaxation. All right? Okay. So far clear? Could you please give me any feedback? I want you to understand every step. Yes?
Yeah.
Okay. Great. So now sign of the terms. So there are some terms in the Lagrangian. So these are the terms. We have these terms, right? By the way, these are m plus m1 terms. These are m2 terms. So this Lagrangian is one term plus m1 terms plus m2 terms. So in total, it's a summation of m1 plus m2 plus 1 terms, right? Okay. Now, let's look at these. Why are they plus? Why are they plus? Why aren't they negative? Let's see. For equality constraint, I can simply, I think I already have written it. I don't need to write it here. If I have this, if I multiply it by -1, I have, because 0 minus times -1 becomes 0. So I can, these are equivalent, right? If I replace minus hix with hix, because you can see it as a new hix, right? As I said, the naming of the function doesn't matter. If you put minus hix instead of this, the minus becomes here. So it means that, or here, it means that for equality constraints, we don't care about the sign, the signs. So you can write plus nu1 h1x minus nu2 h2x, whatever, or make them all negative, positive. Based on your optimization problem, you will decide which one is better for you. Okay, for example, there is one format of the optimization problem which reduces to eigenvalue decomposition. I don't want, this is just an example. If you don't understand it, that's fine. If I write it minus nu or plus nu, in one case, then you will not end up with the correct eigenvalue decomposition format. So you need to have either negative or plus. You will decide which one is better for your case. So that you have freedom in choosing the sign of the equality terms for the equality constraints terms in the Lagrangian. For this simple reason, because when you have hi of x equals 0, you can have minus hi of x equals 0, right? However, the terms for the inequality, the sign is very important. Why? Because when you have this is very different from this, because this means yi of x is greater than or equal to 0, significantly different, right? Therefore, the sign is for inequality constraints is very important. Okay, clear? Okay, great. Now let's interpret Lagrangian. So we defined the Lagrangian. Now let's see what does it do actually. In simple words, let's interpret it. Let's intuitively see what it is doing. So what is our goal? When we have such an optimization problem, what is our goal? We want to first minimize the cost. Of course, we want to minimize the cost, but we have some constraints. So we have some restrictions, but we want to minimize the cost. So our first goal is to minimize the cost. There is but we have some constraints. Let's penalize them. So if our solution to this problem, to this unconstrained problem, isn't satisfying some of the constraints, let's penalize that. Let's have penalty, right? So this is a constraint for each of the inequality. Consider one of the inequality constraints, right? We wanna, this is the penalty for not satisfying y(x) less than or equal to 0. We want to minimize this penalty. Okay, we want to minimize this penalty. And we know that lambda should be greater than or equal to 0. We'll discuss that. The sign we'll discuss about it in a few slides. But accept it from me for now. Assume that dual variables are all non-negative for now. Okay, we'll see why. I want to minimize this. This is a penalty. Penalty for inequality for not satisfying inequality y(x) less than or equal to 0. This is a penalty for this. For penalty for not satisfying hi of x equals 0. So whenever we have some constraint, either we should write it as a constraint or we can have it as a penalty. Okay, now let's add these penalties to the cost. So we were minimizing, we were here, recall this, we were minimizing f of x. However, let's add some penalty terms. Penalty for the inequality constraints. And I'm summing all the penalties for the inequality constraints. Also, this is the penalty for the hi of x. Let's sum them all because we have m2 of them. This is the penalty for all equality constraints. So the cost, penalty for inequality constraints, penalty for equality constraints. We can write it in vector form too, right? And now, rather than only x, our optimization variables are x, lambda, and nu, all of them. And these are vectors, right? x1 to xd, lambda is lambda 1 to lambda m1, nu is nu1 to nu m2, right? So we are adding the objective variables, similar to what we had in linear programming. We were adding stack variables. Here, we're adding dual variables. But what is the benefit of this? Now, we are minimizing this, which is unconstrained. We had a constraint problem. We converted that to an unconstrained. So this is an unconstrained. We don't have any constraint for this, right? Minimizing this Lagrangian. So rather than minimizing f subject to some constraints, let's minimize the Lagrangian, which kind of encapsulates all objective function, inequality constraints, and equality constraints by penalizing or imposing some penalty for it not satisfying inequality constraints and not satisfying equality constraints. Do you get it? And now I think it becomes clear to you why we can call it Lagrange relaxation, because we are relaxing a constraint problem to an unconstrained problem. Okay. And why this relaxation? Because relaxation usually in mathematics makes it easier, right? Why is it easier to minimize the Lagrangian rather than this constraint problem? Can anyone tell me? Why is this relaxation easier? Makes it easier for us. Can you please let me know? Anyone? Hello? Okay.
Only one variable?
What?
Only one variable?
No, we have, see, we are actually we are adding variables. Here we only had x, now we have x, lambda, and nu. But so in terms of number of variables, we are increasing. However, this relaxation makes it easier. Why is it easier?
Is it because we don't have to stick as strictly to the constraints in the problem because we're minimizing it rather than making it strictly equal to or less than?
Yes, exactly. So first off, we are getting rid of the constraints, although we are imposing the constraints in the Lagrangian itself. That's one case. And as you said, so yes, someone also said there are no constraints anymore. However, what is this minimization of Lagrangian doing actually? It's saying that, so what is the difference of these two? Here, if we don't satisfy, if our solution doesn't satisfy this inequality, it's dead. It's a dead solution. We don't accept that at all. So it's a hard restriction. Either do it, either satisfy this or not at all. Okay? Like a hard deadline, something like that. However, here we are allowed to slightly not satisfy that, the inequality. The more we don't satisfy the constraints, the more penalty we have. The more the cost becomes, which is not desirable. That's why we are trying to minimize the penalties. However, the penalties might not be zero, right? So we have soft restriction here. That's why it's called relaxation. We are relaxing hard restrictions to soft restrictions. So whenever we have actual constraints, they are hard constraints. Whenever we have penalties, these are soft constraints. Clear? That's one thing that I wanted to let you know. Another thing is that in the literature, especially in the literature of machine learning, these penalty terms are also called regularization terms. So we are kind of regularizing, right? So this is the function, objective function itself, but we have some M1 regularization terms. These are also the function of x. See, here we have x2. So these are also function of x, although they are function of nu and lambda 2, but they are also functions of x. That's why we have some regularization terms. We are adding them. And when we have regularization terms, the regularization terms are penalty terms, two names for the same thing. And it means that we want to minimize the penalty. And why do we add them? Because the more penalty we have, we want to reduce that. So if we don't satisfy these inequalities or these constraints, they will blow the cost. So assume this is called the regularized or penalized regularized cost, right? So this is cost, this is regularized cost. We want to minimize the regularized cost, but if the penalties are not satisfied or the constraints are not satisfied, it means that the penalties go up, they will blow the regularized cost. Therefore, in order to minimize the regularized cost, we have to satisfy as much as possible the constraints. And as you see, these are soft restrictions. That's why it's also called relaxation. We are making it simpler. We are getting rid of the constraints by adding them as penalties or regularization terms in the objective function. So this is a good technique for changing constraint problems to unconstrained problems if you are not very, very hard on satisfying inequality constraints. But this is interpretation of Lagrangian. So it's kind of, one of the interpretation, it might have other interpretations too, but one of the interpretation is that it's a regularized cost, right? Is it clear? And it has become unconstrained, okay? Now let's go to the next slide. So this is exactly what the explanation of what I said. So let's not go through this, this is exactly what I said. Okay, now let's define another definition. Lagrange dual function, also called dual function. So we can simply say dual function or Lagrange dual function. Usually call it G when the actual cost, they usually call it F. Doesn't matter, it's just naming. Usually they call it G, and it's M1 by M2. Why? Because its inputs are lambda and nu. This is M1 dimensional, this is M2 dimensional, right? And this is defined, this means definition, define as infimum over the domain of X, and your variable for infimum is X. So you are, by the way, infimum is minimum, right? Where you are also considering the case where you don't reach the minimum. Because when you don't reach the minimum, that's not a minimum, that's an infimum, right? So this is more general than minimum. You can look at it as minimum. So minimize this Lagrangian function, but with X, not with lambda and nu. With X, you minimize the Lagrangian function. The Lagrangian function itself is a function of X, lambda, and nu. Over X, let's minimize it. If you minimize that, the optimal Lagrangian function, it means that lambda star, sorry, L star, the optimum, minimum Lagrangian with respect to X is called the dual function or Lagrange dual function denoted by G. And as you see, it's not a function of X. Why? Because you already minimized over X. So you are getting rid of the variable X because you're minimizing over that. So it will be a function of lambda and nu. So far clear? And here I'm replacing the Lagrangian function, infimum of Lagrangian function over X. Is it clear? So usually F is called primal function and G is called dual function or Lagrange dual function, right? Okay. So for convex minimization, when we have a convex optimization problem, and if it is minimization, your G becomes concave. It means that if your F, because in convex optimization, F is convex, right? And you're trying to find this, G becomes concave. If in convex maximization. So if you have such f, your G becomes convex. So in maximization, if it is convex programming, it means that your f is like this. Your G becomes, your f is concave, your G becomes convex. In minimization, convex programming, if f is convex because it's convex programming, your G becomes concave. So you need to know these cases. For maximization, G would be supremum of Lagrangian, right? But we are, as I said in the first slide, even if we have maximization, we can convert it to minimization. Here we are talking about minimization only. So assume we are minimizing the primal function f. Now the dual function would be minimization of Lagrangian. Okay, primal and dual feasibility. So far clear? Can you please give me feedback? Yes?
Yes, yes.
Okay, great.
Yeah.
Great. Now, do you remember about the feasibility set that we discussed? Now we are repeating that, but now we have primal optimization problem, the primal function and dual function. We discussed about primal function and dual function. That's why we have primal feasibility. Okay, what is it? It means that the solution of this optimization problem is an optimal point denoted by x star. Assume that, this assumption. We denote it by x star. And this, the optimum cost would be f star. So f of x star, let's denote it by f star, right? And this is optimum function, right? Or optimum value for the function. And the optimal point x star, which is the argument satisfying the constraints, is one of the feasible points which minimizes the function f. Of course, it's feasible point because it needs to satisfy the constraints, satisfying the constraints in problem 1. So it means that it satisfies each of the, it means for all y1 to yn1, it is satisfying the inequality constraints. For all m2 equality constraints, it's satisfying the equality constraints, right? And for all of them. So it's satisfying all of the constraints. It's called primal feasibility. So it's feasible. And why do we call it primal? Because we are minimizing the primal function. So far clear? And these are the constraints in the primal optimization. Okay. Now let's talk about feasibility in dual function. So this was the optimization problem that we started with. This is the Lagrangian for this optimization problem, or Lagrange relaxation. The optimal point x star minimizes the Lagrangian function, because we know that because Lagrangian is a relaxation of the optimization problem to an unconstrained problem. It minimizes that. But let's see. Okay, on the other hand, see, consider that. According to equation 3, what was equation 3? The definition of dual function was equation 3, which was g of lambda and nu equals infimum of Lagrangian, right? Let's repeat it here. This is equation 3. Definition of dual function. I'm repeating it here. The dual function is the minimum of Lagrangian with respect to x. This is exactly it. It means the minimum of Lagrangian with respect to x. So this is the definition of dual function. On the other hand, we know that x star is a solution of primal problem. It is satisfying the hard constraints, restrictions. Of course, it will satisfy the soft restrictions too, because when you satisfy the hard constraints, of course, the soft constraints are satisfied too. Therefore, you can write it in this way. you know that the solution of this x is x star. So you can say Lagrangian of x star, lambda and nu, is exactly the dual problem. The dual function, sorry. The dual function equals the minimum of Lagrangian with respect to x, but we know that x star minimizes the Lagrangian. Why? Because it satisfies the hard restrictions. Of course, it will satisfy the soft restrictions in the relaxation of Lagrangian. So it is a minimum for Lagrangian too, when we are minimizing with respect to x only, okay? Which is a definition of dual function. Is it clear? Is what I have here. So this consists of two equations. This, according to the definition of dual function, and this, according to the discussion that I just had. I said x star is a solution of primal problem. It satisfies the hard constraints. Of course, it will satisfy the penalties. Therefore, it is the solution for minimization of Lagrangian with respect to x2. So combining these two equations gives us the whole thing. It means that dual function equals the Lagrangian of x star, lambda, and nu. Is it clear? Yes?
Yes.
Okay, great. Now, lemma. First off, let me tell you, because some of you might not have heard of these things, lemma definition and these things. So in parentheses, I'm saying this. Don't worry about these names. These are fancy names, and these are for organization of mathematical papers. Why? Because when you write all of the expressions and proofs and everything back to back without any sections and these things, sectioning, it will be very confusing to understand the theory. Therefore, mathematicians have come up with a solution to organize their papers. They said, okay, let's have sections of the theory, saying that lemma, and what is lemma? Lemma is that a section of the theory that you claim something and you have proof for lemma. So lemma, you claim something, you prove it, you have another lemma, you prove it. So see, you have sectioned or partitioned your paper into several parts. Now it's easier to understand. Okay, now in this lemma, you want to prove this. In the other lemma, you want to prove this. Why do you call it lemma? Lemma is usually says that after solving and proving some lemmas, then usually you propose or claim a theorem. Theorem is a more important lemma. So you have several lemmas, and at the end of the paper, for example, you have one theorem which uses the lemmas. So lemmas are going to be used in a theorem usually. So you prove something as a lemma, you prove something as lemma 2, but in theorem you will claim something, but in the proof of the theorem you will use lemma 1, and you will also use lemma 2 in order to prove your theory. Theorem and also proposition is kind of the same as theorem. So proposition and theorem are kind of bigger picture. So what is your paper shouting? So lemmas are not necessarily what the paper is shouting. The paper is shouting something, some theory. It says that, okay, I'm claiming this and I'm proving this. Usually you have 1 or 2 theorems in the whole paper, but you might have 10 lemmas because you're going to use different lemmas in one theorem, something like that. So the definition is also when you define something. So you have definition, you have lemma, you have theorem or proposition. Also, there is another thing, corollary. Corollary. What is corollary in mathematical papers? Corollary means consequence. So when you have something, lemma or theorem, whatever, you might have some consequence. Based on what we just proved in the previous lemma, we have some consequence. Consequently, or in conclusion, we also have this. So we usually write a corollary. Corollary is another name for consequence. Usually, because they are consequence, they don't have any proof because it's consequence of the other lemma. But sometimes it needs proof too. So these definition, I said that corollary, lemma, proposition, theorem. These are the most things. Sometimes people write lemma as claim. So they say claim 1, claim 2. And these are different naming for the different sections. So now I close the parenthesis. I wanted to know what lemma and these are. Okay, now lemma. Dual function as a lower bound. Okay, for minimization problem, if the dual variable is, so what does it mean? That all elements of lambda, it means that lambda 1 to lambda m1 are greater than or equal to 0. Do you remember this is generalized inequality for vector? Okay, then the dual function is a lower bound for f star. It means this. This is the English explanation of this equation, of this inequality. It means that the dual function is a lower bound for f star. F star is f of x star. Do you remember we defined that? It means that the optimum cost function. Optimum cost function is always greater than or equal to g of lambda and nu. Is greater than or equal to the dual function. It means that when you have f, this is f star, right? Whatever your dual function is, it's below this f star. It can't go above that. So your g is always below that. So otherwise, in other words, g is upper bounded by f star, or g is a lower bound for f star. Okay, let's see the proof. But this is the condition. Lambda should be greater than or equal to 0. Let this, which means that for all I, lambda I is greater than or equal to 0. Now consider a feasible x tilde. It's just a name, doesn't matter. A feasible solution, right? It means that it satisfies the inequality, the constraints. Now let's put this x tilde in the Lagrangian. What is equation 2? So this is the equation 2 is the definition of the Lagrangian. Based on the definition of the Lagrangian, I put x tilde in the definition of the Lagrangian, right? Okay, now let's talk about it. Hi of x tilde is 0. Why? Because we said that it's a feasible point. And one of the constraints is that hi of x should be 0 in order to satisfy the constraints. So we know that hi of x tilde is 0 because it's a feasible point. It's in the feasibility set. It satisfies the constraints, all of them. Also, it's a feasible point. Therefore, yi of x tilde is less than or equal to 0 because yi of x, the constraint was this. Also, the constraint was this. These should be satisfied. That's why this is 0. This is less than or equal to 0. Right? When this is 0, it means that this term is 0. So we get rid of this term. When this is less than or equal to, and also we assumed that lambda i's are greater than or equal to 0, it means that this term is less than or equal to 0. All of them. So when you sum, you are summing several negative scalars. So the sum also becomes negative. Right? I mean non-positive. Non-positive scalars, the sum becomes non-positive. Therefore, so this is less than or equal to f of x tilde. Why? Because you are saying that f of x tilde plus a non-positive term plus 0. Of course, it's less than or equal to f of x tilde. So far clear? Okay. I'm saying that here we showed that Lagrangian is less than or equal to f of x tilde. Let's rearrange it. It says that it means that f of x tilde is greater than or equal to Lagrangian. Lagrangian of x tilde. Now, so we proved this part. Now let's talk about this. Lagrangian, of course, the infimum of Lagrangian over x is less than or equal to Lagrangian for x tilde. Because this is exactly the definition of infimum or minimum. For understanding infimum, assume it's the minimum. Minimum of lambda is less than a lambda. Of course, I think this is true. This is obvious for you. Minimum of f of x over x is less than or equal to f of x for all domain of x. Because it's minimum. So minimum of Lagrangian is less than or equal to Lagrangian for a point x tilde when the minimum is over x, right? Okay, so we prove this too. So we prove this based on here. We prove this too right now. Now let's see. What is this, by the way? This is the definition of the dual function. So we prove this too. This is by definition. This is by definition. We proved this, we proved, so we proved this, we proved this, and this is by definition. Now let's see the whole thing together. What does it mean? That G is less than or equal to f of x tilde. What we wanted to prove. Right? So it means that for all domain of x, then sorry, doesn't matter. So because this side is based on domain of x and this side is based on the domain of lambda and nu. But let's not talk about the domain. Let's talk about the function value. So f star, it means the minimum of f is always greater than or equal to g in everywhere. Obviously, this also means that g star, which is the maximum of g, is less than or equal to f of f star. From this, we can conclude this too, because when g is always less than or equal to f star, its maximum is also less than or equal to f star. So far clear? Now, I think you understand what I was saying in dual linear programming, the dual function for linear programming in last session. I said this never happens. Assume you have two balls, the gap is either 0 or non-negative, 0 or positive. The gap can't be negative. If you have two balls, can see my hands. If you have two balls, this never happens. It's either two balls are like this or the gap is positive. That's the reason. We just proved it. So far clear? Yes? Okay, now see here. Great. So see here. For minimization problem, when we have f, we are minimizing this. So this is f star, right? This is f star. And g is like this. So we have g star. By the way, they are not necessarily convex and concave. I'm just showing, I'm depicting it. I'm illustrating it. It might be something like this. Doesn't matter. I'm talking about the values. This is f star. This is g star. Okay. So there is a gap, and this gap can be 0, but it can't be negative. If for maximization, we have the other way around. We are minimizing g, but we're maximizing f. Again, we have some gap. The gap might be 0. But let's focus on minimization right now, because we assume that the optimization problem is minimization. If it is maximization, we can convert it to minimization, as we discussed. Okay. Again, consider two bowls. From the above lemma, so we conclude that, by the way, do you remember in the lemma, we assumed that we also use this assumption here, right? We assumed that lambda i's are all non-negative, either greater than or either positive or 0. Here, we assumed that. Therefore, that's why now it clarifies why I said in several previous slides, assume that the dual variables are all non-negative. Because of this, we need to have this assumption to have this condition, to have non-negative gap. Okay. Again, here. It means that for inequality constraints, because for equality constraints is that we don't care. Do you remember? We could multiply the equality constraints by -1. And this -1, let's go back to that. Just let me bring it. No, it was here. Yeah, here. Okay. Here we said that if it is negative, we can say negative comes here. Or there is an or. we can make it positive, but absorb the negative into the dual variable, and then rename this minus nu I to something else, such as zeta I. Whatever, doesn't matter. The naming doesn't matter. Like Zi, whatever. So define minus nu I as Zi. Therefore, the sign of the dual variable for the equality constraint that doesn't care much. But for inequality constraints, the sign matters. They should be non-negative, because we want to have non-negative gap between the primal function and the dual function. Optimum, they're optimum, right? Okay. Now let's go back to where we were. So this is exactly what we discussed. By the way, we assume that, okay, so if the inequality is greater than or equal to 0, we can treat it in this way. We can say its dual variable must be negative now, the other way around. Why? Because minus yi is less than or equal to 0. So when we have less than or equal to 0 inequalities, their dual variables should be non-negative. When we have greater than or equal to 0 in inequalities, the dual variable should be less than or equal to 0. I'm talking about minimization. We assume that you are minimization problem, right? So this assumption is for greater than or equal to inequalities for minimization. In minimization, if we have this is for less than or equal to inequalities. If we have greater than or equal to inequalities, then their dual variable should be non-positive, right? Clear so far? Right? Okay, I think it's now when you are understanding the reasoning behind the different things, it becomes very interesting to you what optimization is saying actually. Okay, now dual problem. So primal problem and dual problem. So we saw that the dual function is a lower bound for the optimal. We saw this, right? We just proved it. We want to find the best lower bound. Let's find the best lower bound, because there is a gap. For example, here, there is a gap. Let's find the least amount of gap, because here is also a gap, right? Let's find the least amount of gap. It means that let's find the gap between f star and g star, between minimum of f and maximum of g in minimization, and the other way around in maximization. Okay, so let's find the best lower bound. Therefore, let's maximize g of lambda and nu with respect to dual variables. Why? Because its inputs are dual variables. So let's maximize this g with respect to lambda and nu, subject to lambda is all lambdas are greater than or equal to 0, because of that assumption that we said. We said that dual variables for inequalities should be non-negative. Okay, so this is a constraint optimization. This is dual. This is dual. This is Lagrange dual optimization problem, or in short, it is a dual problem for optimization 1. And optimization 1 is the optimization problem that we started with. I don't go back to the first slide. Okay, so that optimization problem that we started with is called primal optimization problem. So the primal function f was used in primal optimization problem. The dual function g is used in dual optimization problem. So don't confuse dual problem with dual optimization. This is dual optimization. This is dual problem. F is primal. So this is dual optimization problem or dual problem. This is dual function. F is primal function, but minimize f with subject to the constraints is a primal problem. Okay. Now the variable, the optimization variable of primal problem is called primal variable. So X is here primal variable. The optimization variable of the dual problem is called dual variable. So three things we are discussing, you shouldn't confuse: primal function, primal problem, primal variable. F, minimize F subject to constraints, and X. The other three things: a dual function, dual problem, dual variables. G, maximize it with subject to lambda greater than or equal to 0, and lambda and nu. Right? So, okay, and let's call the optimum dual variables lambda star and nu star. For optimum primal variables, we called it X star, right? Do you remember? Now, let's call the optimum dual variables, which maximize this G, satisfying this constraint. Let's call them lambda star and nu star, and put them in G. We denote it by G star. Exactly. Do you remember we denoted f of X star by F star? Now let's denote G of lambda star and nu star by G star. What is it? It's supremum or maximum of G subject to lambda is greater than or equal to 0. Right? Any question? No? Okay. Weak and strong duality. So I think it has become so clear to you. The gap is non-negative. It's either 0 or positive. If the gap is, so the gap is this. It means that the gap is either 0. It means that either G star is F star or G star is less than F star. Right? This is called weak duality. This, the gap is 0, is a strong duality. Here, a strong duality. And what does it mean? This means this: G of lambda star and nu star, which is maximum of G, equals F of X star, which is the minimum of F. And it in minimization, maximization is the other way around, right? And this means a strong duality. Okay, let's see some shapes for it, some figures. So again, here, do you remember this shape, this figure? FG, this is F star, G star, a positive gap. This is weak duality. When F star matches G star, it's a strong duality. And for minimization, for maximization is the other way around. G, we are minimizing G, we are maximizing F. And this gap is either positive or 0. It's weak duality or strong duality. So far clear? Can you please give me a feedback so I know how it's going?
Yeah, it's clear.
Clear. Okay, great. So assume that the optimization is iterative. So we start with some solution. We will see some iterative algorithms soon. But assume, what do you mean? What do I mean by iterative optimization? It means that we don't find the solution right away. So an example of finding the solution right away is that assume that you have a convex function f, you minimize f, and there is no constraint. Assume you have f of x, minimize f of x with respect to x, no constraint. What would you do to solve this? Can anyone tell me? Assume you are given this problem. This is convex. And you want to find this. Can you give me this? How do you solve this? In high school, you learned that you have a function, you want to find its minimum. Assume you have a quadratic function. What do you do for finding its minimum?
We integrated.
No, the exact with the opposite. We take
Differentiate.
derivative. Yeah,
Yeah.
we differentiate it. We take derivative and set it to 0.
Uh-huh.
Do you remember? Yes.
Yeah.
This is exactly, yeah. For finding extremum of the function without any constraint, we take derivative and set it to 0. If it is convex, we only have we have one optimum solution. Especially if it is strongly convex, we'll have one x star. If it is not convex, it might be not convex. It will give us several solutions. We check. First we check which ones are stationary saddle points, and we exclude them. And then among them, we say which ones are maximum, we exclude them. So we only have minimums. Now let's get the f x star with the minimum, the least amount of f. That would give us a solution. Assume I take derivative of f of x with respect to x and set it to 0. It gives me x1, x2, x3, some solutions. x1 is a saddle point. Again, x2 gives me maximum because it might be maximum. It might be saddle point, might be so saddle point, maximum, minimum. Assume that x3 and x4 are both minimum. x3 and x4. Among these, I get the one which has the least amount of f, right? Assume f of x3 is less than f of x4. So I get x3 as the answer. If there is no constraint, we can simply do that. If we can take the derivative and set it to 0. Sometimes f is so complicated that when we take derivative and set it to 0, we can't find x in the left-hand side and the rest in the right-hand side. For example, when you take the derivative, it becomes this tangent of x plus square root of sine of x over x2 plus 1 equals 0. How can you find x out of this? Of course, using numerical iterations, you might find numerical analysis. You can find a root for this. But finding a root for this is very hard, right? So if it's finding the root for this equation is not hard, you can simply do that if you don't have constraints. Exactly what we learned in high school. But if it is hard to find the roots, or if we have constraints, then we need to have iterative optimization. It means that we start with something, we start with some solution, and we try to move toward the minimum. We will study several iterative algorithms in this course, okay? And we go until convergence. So that's one thing that I wanted to let you know. Okay, and the series, so the series of optimal solutions. So in each iteration, we have some solution, right? In iteration 0, for example, we have x of 0, then we have x of 1, x of 2. So we are finding some x's. We go until we converge to x star. As example, we start from here. This is x. This is x0. We go with some step. This is x1. We go until we reach here. This is a good. We might not, if it is convex, it's easily converges to x star. It means that this is x0, this is x1. We go until this is x star. So we are converging to x star, right? If it's not convex, we might get stuck in the local minimum. Okay, so we have some iterations, solutions in different iterations. Likewise, for maximization of the G dual function, we can do it iteratively. So we'll have nu 0, nu 1. We also have nu 0 and lambda 0. We'll have nu 1 and lambda 1. And nu converges to nu star, and lambda converges to lambda star. And in nu star and lambda star, G is maximized. In x star, F is minimized, right? That's why in each iteration, assuming that the F is convex, it's a convex optimization problem, then we will definitely have this. if it's not convex, you might have some oscillations. It means that sometimes this might be more than this, but eventually the pattern is the same. So the pattern is saying that either the pattern, or if it's it's a convex problem, exactly it is decreasing. F is decreasing until we reach f of x star. That's why we are saying that in x star, the value of f is minimum. Also, nu and lambda. We are starting with this. It has some g. We are increasing that. We are maximizing g until we reach some point. And there is a gap between f of x star and g of lambda star and nu star. But the gap might be 0. If the gap is 0, this is a strong duality. But this is weak duality. Is it clear? So iteratively, we are also moving toward the solutions. Although if it's not a convex problem, it means that we might have some oscillations, right? We might come to here, to this point, go up again a bit, and go down, down, down. So we might have some oscillations, but the pattern, the overall pattern is decreasing. The overall pattern for G is increasing. If it's convex, not only the pattern is decreasing, it's actually decreasing. Right? Is it clear? Okay. Now let's talk about the Slater's condition. Lemma. Slater's condition. For a convex optimization problem in this form, assume that we are minimizing f, you have some inequality constraints, and your equality constraints, let them be like this, because you can write equality, so for I 1 to M2, you can write all of them in this matrix form. Do you know why? Let me think. Sorry, 1D. Yes, M21, M2D. So let this be M2 by D. This is a D-dimensional vector. This is M2 dimensional vector. We can write this in this format because A11 x1 until plus 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 A1D xd equals B1. Also, to do it for M2 rows, you will have until you will have M21 x1 plus 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 AM2 d xd equals BM2. So you can write it in this matrix form. Okay, this is one thing. For you will have a strong duality. This is what a Slater's condition is doing, is saying. You will have a strong duality if it is strictly feasible. It means that for the inequality constraint, okay, for the inequality constraint, it is strictly feasible. So it's not less than or equal to, it's exactly less than. So it means that there exists at least one point in the interior of the domain X, right? We already defined interior and the domain. There is some point in the feasibility set where the inequality constraint is satisfied without equal and also satisfies the equality constraints. So in simple words, if you can find a point which satisfies equality constraints and the inequality constraints without equal for all of them, it means that for all of the inequality constraints, the equal is not it is not on the boundary. Okay, then if you can find at this one point, it means that you will have a strong duality. This is a good lemma. Then it means that if your problem satisfies this Slater's conditions, it means that you can, for finding f star, you can find g star. You can find form the dual optimization problem, solve g, maximize g rather than minimize f, subject to constraints. and you will be sure that whatever G star you have, F star will be that, right? So that's a good point. The strong duality is very important. However, if you have weak duality, you can't be sure. You know that G star is less than F or equal to F star, but the gap might be positive. Okay, an example for a Slater's condition. This minimize x1 squared plus x2 squared. Assume that your optimization variables are x1 and x2. x1 squared plus x2 squared plus 1, subject to these two constraints. Okay, this is an example. Let's see if we can find at least one point x1, x2 which satisfy this inequality constraint. This I will correct that. So this should be exactly less than 0, and this should be 0. Let's find that. Okay, we can solve these system of equations. So x1 minus x2 minus 2 equals 0. So we can write x1 as x2 plus 2. Let's put it, substitute it in this, and we'll have this. It means that x2 should be greater than minus half. Okay, an example is 0. x2, let's take x2 0 and then put it back in this. So we'll have this x1 equals 0 plus 2. So x1 is 2. Therefore, we found this. I said at least one point. There exists at least one point. It satisfies it. Therefore, it satisfies the Slater's condition. Therefore, strong duality holds for this optimization problem. It means that if you find its dual optimization problem and find its G star, F star equals G star for this problem. And Slater's condition usually holds for engineering problems. For simple engineering problems, usually we have a strong duality, and that's the interesting thing. Okay, any questions so far? No. Okay.
No.
Yes. You were asking some question?
No, I said everything's good. Everything's good.
Okay, great. So I think in the last, let me see. Yeah, let me explain this also, and then I will talk about briefly about the. Let me leave this for the next session. So far we covered Lagrangian function, and so far we covered preliminaries, and then linear programming, then integer linear programming, and then sensitivity analysis. Also, we covered Lagrangian, dual function, primal function, all of these. And starting this slide, we'll have KKT conditions, but it highly relies on whatever we just talked about, the Lagrangian. So Lagrangian is the most important thing in KKT conditions. And okay, your midterm exam will be until the end of KKT. So the lecture of KKT conditions. It means at the end of these 42 slides. So a portion of the next session will be in your midterm, and that's so it will be preliminaries, linear programming, integer linear programming, sensitivity analysis, Lagrangian, and KKT conditions. I think we'll have one problem from KKT conditions and Lagrange, the method of Lagrange multipliers, and it's very simple. I have provided an example at the end of this this slide deck, and I'll try to make the question similar to that, so not to have any surprises. So that's one thing. Also about the so let me stop sharing and you see me. So about the project. So please, I think that would be best. I will post an announcement soon, saying that what you should do. But what I'm going to ask you is that I'm gonna make some spreadsheet or some paper template for you to make announce your team members. And I thought about the number of people per team. So I think we so far we are 33 students, and in order to have all teams to present about 20 minutes, including the question answering. In the last session, I think it's good to have maybe 8 teams. Therefore, we'll have about teams of 4 members, and one of the teams can be 5 members. Is it good? So if you have any suggestion or anything, feedback, please let me know. But this is what I came up with. I think it's good to have 8 teams. Each team has 4 members. One team can have 5 members. And then you will choose, I will say that the details in the announcement, but we'll have, yeah, also people are saying it's good. Okay, great. Milad is saying, Khashar is saying good. So yeah, I think it's good to have members. And so now in this project, you will also, in addition to optimization and cool stuff, you will also practice team working, because this is important for both industry and academia, how to do team working. And I recommend that everyone in the team should do something in the project. Shouldn't be that someone or some people work for the whole team. You need to collaborate together. And this is what I expect. And also at the end in the presentation of your projects and your results and whatever, I expect everyone to talk, to have a portion of the talk. You can have a collaborative talk or whatever you decide, but everyone is good to present, and that the presentation will also have a portion of your grade. But I will not be very hard and picky on that, but I want everyone to present and the findings and also whatever you have done. So the project can be anything related to optimization. So anything that uses optimization. It can be for people who like theory, you can work on the theory of optimization. If for people who like practice, you can work on some practical problem which uses optimization. So I totally give it to you to choose your subject, but we need to have some proposals. I mean, 1-page proposal, explanation of what you are going to do. And I will make a Dropbox folder for that. You will put, I think that I thought about the deadline for that too. Let me look at my calendar. I think the good thing, so I think February 24th for the proposal of 1 page. So until February 24th, you're gonna have time to choose a topic and also find the team members, form the teams, and also find a topic that you consensus, all the team members consensus on, and then write a proposal of what you're gonna do, the details, and what you expect to have. And these things, again, either it's theory or practical practice, depends on you, whatever your interest is. And then the proposals are for me to know that what you're gonna do, so it's not very off topic. If it is, I will say that please change it or please modify it. So yeah, that's the thing. And at the end, you will write a report, and we'll have a Dropbox folder for that. And also you will present, and everybody in the will present in the presentation, everybody in the team. And we'll have also at the end, several minutes at the end of each presentation, we'll have Q&A. So people ask questions and you answer and these things. Is everything good? Any question?
Sounds good to me. How are we gonna pick the 4 group members? Like, are we all just gonna, I guess, chat, or are you gonna assign?
No. It's you choose. I'll give you freedom to choose based on your interests. So try to find people who have the similar interest like you, and you will form the group. You can in the teams that we have, teams group in general. Q&A is for question answering, but in general you can say, hi group, hi class, I have this interest. Who likes to be my team member? You can chat, or you can chat privately with each other. If you want to do it publicly in the teams group chat, you can do that. You can also privately message someone on Teams or email saying that you want to be my group member and these things. No. Khashayar has asked, so the deadline is 24th February to make group and get ready for proposal. Yeah, yes. So until February 24th, you should have given the names of the team members as well as the proposals, both. Yes. So it's more than 2 weeks. I think you have time to decide on all of this. How many members can form a team? 4 members a team, but you are 33. Therefore, one team can be 5. But we won't have. It shouldn't be like a team of 3 and a team of 6. It should, the number of people in teams should be uniform. I don't want to be different. So all teams will have 4. One team can have 5. Okay. Okay, I think everything is clear. Any suggestion or feedback?
Hi Ben. So actually
Hi.
wanted to confirm, like for the midterms, like we will have the preliminaries as well for the exams.
Yes, and
Okay.
it's I will try to make it not very hard. So don't worry, but try to understand the assignment and also the lectures. So don't skip the
yes.
lectures. Don't
Yeah.
skip the lectures, and please understand the lectures. Practice with what we have said. Also work on the assignment very hard. Try and understand it. Don't leave anything without understanding. If there is ambiguity, please ask, either in class or in the teams, and I'll try to be responsive. Was the course clear and understandable to everyone?
Yeah.
Yeah. Okay, great. Yeah, I think the importance is that you understand things, because this course can be not understandable, but we are trying to make it understandable. And I think when it becomes understandable, it becomes very sweet. It becomes very sweet. Yes, and that's the thing. We want to understand the reasoning behind things so we can enjoy optimization. When I learned optimization, when I understood the reasoning and things behind it, at the end, I sat down, in my mind, I looked at the landscape of optimization. By landscape here, I mean, I put different optimization algorithms next to each other, and I thought how they are connected to each other. And that was the point, the kind of enlightenment that Buddhism and these things say. An enlightenment came to me that, okay, oh, by the way, they are all connected using KKT conditions, and why this is working because of this is because of it. So when you learn these algorithms all together and you put them together and you will see the connection between all of them, then optimization becomes very sweet to you. Yeah. Yeah, and Khashayar has said, yes, we try to understand more since this course is new. Yeah, I think, yeah, again, look at the optimization course in this way, that you learn the reasoning behind different parts, and then at the end, you look at all of them together and try to find the connection, to understand the connection between them. And then you will enjoy that. That's the nirvana of optimization, I can say. Okay. Is everything clear now? Okay, any question? Or should we conclude the session? Right?
I
Okay.
think I'm good. Thank you very much.
Great. Thank you very much. Okay, have a good night. Thank you.
Thank you. Have a good night.
Thank you. Have a good night. Bye.
Thank you.
Thank you. Thank you.
Thanks, Ben. Bye bye.
Thank you. Bye. Bye. Thank you.